And the person who really pioneered some of these very early architectures is John von Neumann in the 40s. And he sort of described the following sort of basic architecture for a programmable, electronic computer. He started off with a central processing unit, which contains the data path that we've described. Some small number of a little bit of finite storage, some small number of registers that sort of represent the current state of the computation inside of the CPU, and then some way of manipulating the values and generating new values, which can be loaded into registers and cycle again and again and again. So that's basically, think of it as just a little finite state machine. Left to its own devices, there'd be a limit to what that machine could do. We're going to add a main memory, and think of it as having memories are organized in terms of think of it as an array of locations, and each memory location will have a certain number of bits of information in it. So we're going to send an address to the memory to tell it which location we want, and it will return to us all the bits in that particular memory word, that particular element of the memory array. Okay, and the idea is now this is, even though we have some small little finite scratch memory inside the central processing unit, conceptually this can grow quite large. And in fact, most of you own machines that if you felt rich and famous, you could go out and plug more memory into, unless you have an Apple machine, in which case they've soldered it on the board and Steve Jobs has already figured out how much memory you get. But conceptually, we could make the memories bigger and bigger and bigger. With a 64-bit machine, we could spend a lot of money plugging in more and more memory chips if the actual electronic board. But from an architectural model, we wouldn't change much inside of here if we, to add more memory, we'd just have a larger capacity. We'll say more about some of the limitations of what's actually built into here in a couple of weeks. So we're going to talk more about memory systems later. Okay, so that memory is sort of our stand-in for an infinite tape. And we're going to substitute, instead of infinite, we're basically going to be able to talk about expandable storage. So conceptually, we can make as much memory as we want, although we're not quite at infinite yet. And then finally, we'll add a couple devices that will allow us to get answers into and out of the machine. So you have network interfaces and screens and keyboards and stuff like that. And so that's what makes all of the computation interesting, is that we're able to feed it values and get back answers. Okay. So how does it achieve programmability? I mean, what about the diagram I just showed you meant that you could change what it does? And what von Neumann's insight was the idea is memory is not going to only be sort of a place to put data, okay, but it's also going to be a place to put the actual instructions that tell the machine what it should do cycle after cycle after cycle. So the machine will actually reference memory for two pieces of information. One is any data values that it needs to read and write from its local scratch memory. And the second thing is that's where all the instructions that tell it the sequence of operations. So the idea is, instead of building that into the read-only memory that inside the FSM here, we're going to design an FSM here who will go out and actually get an instruction from memory, which will be bit-level encoding of the operation we want to have performed. And then we'll do that. And we'll perhaps change some values in the scratch pads or the scratch memory inside the CPU, or maybe update a memory value. And then we'll go back to memory to get the next instruction. So there'll be this notion of a current instruction. So we'll have a separate little piece of the machine whose job it is to keep track of what instruction we're on, where in memory we should get the next instruction from. And at least conceptually, we'll just increment that index of the next instruction index from, as we step through the program. And perhaps if we do loops and stuff, that index will go back and so forth and so on. Okay, so what we've built in here is really an interpreter, okay, a little hardware interpreter whose job it is to pick up a set of operations to do from memory, do them, and then continue. So in some sense, this is sort of like a universal Turing machine, right? It's referencing the tape not only for the data that the program is operating on, but for the sequence of operations that make up the program. Yes?
So for a little factorial
Yes.
The hardware was specifically, like you had a times and a minus.
Right, so we're going to actually build ourselves a much more interesting repertoire of instructions and hope that we can use them to, do any computation that we want. And today and next time, we'll spend a little, we're going to be agonizing over whether our list is complete. Do we have everything we need? And it turns out the list is surprisingly short and sweet. And in terms of the sort of computations the machine can do.